Welcome to the AP Physics C pre-flight on Schwarzschild radius and escape velocities from the Universal Gravitational Orbit Unit. Our group members are Sai Changovala, Braden Creel, and Sarah Susanto. By now, you should have already learned about the law of conservation of energy, a little bit about rotational motion, kinetic and gravitational potential energy, but today we will focus on black holes and the Schwarzschild radius. A black hole is essentially a large mass which causes a region of space having a gravitational field so intense that no matter or radiation can escape. Meaning, a region where there's a massive object that creates a gravitational pull that stops even light from escaping. Every large mass has a Schwarzschild radius, which is the distance from the center of the mass to the point on the edge of the mass, which the gravity weakens enough to where objects are not impacted by the gravitational field. Although planets and other large masses may have a Schwarzschild radius, we will focus specifically on black holes for this pre-flight. Every black hole is an escape velocity, essentially the lowest velocity that a body needs in order to escape the gravitational attraction of a particular planet or other object. In essence, the velocity an object needs to escape the Schwarzschild radius. Black holes are unique that their escape velocities are faster than the speed of light, which causes the phenomena we see surrounding black holes. Moreover, the Schwarzschild radius for black holes is less than the radius of the mass itself, which indicates that no light and absolutely no matter can escape. The escape velocity can be derived using the equation from the AP Physics C tables and equation sheet. Using the law of conservation of energy, the total object of the object leaving the mass at the surface must equal the energy of the object once it has escaped the gravitational field. The energy once escaped is approximately zero, since we want to find the smallest possible velocity needed to escape. We can say that the energy is equal to zero because at the end of its route, the object will have no velocity and would have just escaped the gravitational energy pull. We use the equation to substitute in the equation for potential and kinetic energy. So establishing the law of conservation energy states that kinetic energy at the surface plus gravitational potential energy at the surface must equal the kinetic energy escaped plus the gravitational potential energy escaped, which we have already established is equal to zero. Through manipulating the equation, we can set kinetic energy at the surface equal to the negative potential energy at the surface. As you see here in your equation sheet, the potential energy equation for gravitation is already negative, turning this side of the equation positive. Once you've substituted the equation into the kinetic and potential energy system, we receive 1/2 mass of the object times velocity escaped squared is equal to g, which is the gravitational constant, which is equal to 6.67 times 10 to the negative 11 times mass of the object times mass of the large mass divided by r, which is the Schwarzschild radius. As you can see in this stage, the mass of the object is irrelevant to the velocity escape because the gravitational energy and the kinetic energy equations hold the mass of the object. Once manipulating the equation, you see that velocity of the escape is equal to the square root of 2 times g times the mass of the large mass divided by the Schwarzschild radius. When talking about light or objects leaving a black hole, the mass of the large mass is the mass of the black hole. Inside the Schwarzschild radius of a black hole, the escape velocity is greater than the speed of light, which means nothing can escape the black hole's gravitational field. The Schwarzschild radius is also known as the event horizon. Since the black hole's Schwarzschild radius is less than the radius of the mass, no light can escape for black holes. The Schwarzschild radius can be determined using the escape velocity equation. You set the escape velocity equal to the speed of light and solve for r. Next, you will learn Kepler's equation and more on planetary motion.